All right, this is the second question from the 2018 Physics C Electricity and Magnetism free response section. Again, it's available on the College Board website, and I've posted it down in the notes if you want to get the copy of it. That website also has the grader rubric and chief reader questions for it if you want to listen to it. And once again, the best way to use this video would be to try to work out this problem before I talk about it, and then check your answers against what I'm saying. So here we go. We have an experiment, and it's to measure the dielectric constant of paper that has an area that's given there. We're going to use aluminum foil. Two parallel plates are created with the same area as the paper. We got 500 sheets of paper that are placed between the plates to give us a capacitor as shown in the figure above. So we're going to take a multimeter. We're going to measure the capacitance with the multimeter. It's a fancy multimeter. The number of sheets and total thickness of paper are recorded below. The experiment is repeated, and we're just going to pull out paper each time, giving us a different distance and a different capacitance. So what we want to do is take these data with sheets of paper, the distance separating them, the distance separating the parallel plates, and the measured capacitance. We want to take that, and we want to graph it in such a way to get a straight line whose slope could be used to calculate a numerical value for the dielectric constant of the paper. So what we have here, what we know about capacitance, it's A times epsilon over D. So if we're talking about a dielectric constant, it's A times kappa, the dielectric constant, times epsilon naught over D. So if we're going to graph this stuff, capacitance is going to be A epsilon naught over D times kappa. What we're going to do, since we have the capacitance and the distance separating them, our graph is going to be capacitance as the y value and 1 over D as the x value. So on my vertical axis, I'm going to put the capacitance, and on my horizontal axis, I'm going to put 1 over the thickness. And so I want to go through and here put 1 over D, so that's going to be meters to the negative 1 in that column. So I'm going to take that distance and I'm going to take the inverse of it all the way down the column, because I'm going to use those numbers to make a graph. So I've got 22.2, then I have 27.8. I'm going to take the inverse of that. We have 37.0. The next one we have 55.6. And the last one we have 100 point. It's not necessary that you do significant figures, but in this case it's good to be a little bit reasonable with it. Now that we have this, our values, we're going to be graphing this on the y-axis, and we're going to be graphing that on our x-axis, which is what the next part is. Plot the data points for the quantities indicated in Part A on the graph below. Clearly scale and label all axes, including units, as appropriate. So, let's say you didn't know what to graph in Part A. Part B, as long as you stay consistent with what you said in Part A, you're going to get almost all of the points for this graph. But we said that we would put the capacitance measured in farads on the vertical axis, and that we would put the 1 over the distance separating them, meters to the negative 1, on this axis. It's telling me to label the axes, so that's the first thing that I need to do. I need to write down what's going on the axes and the unit that goes along with it, including units if appropriate. We've got units for all these. Then we need to scale the data. I see that my capacitance goes from 6.5 to 21. So what we're going to do is say that this is 5 times 10 to the negative 11th. This is 10 times 10 to the negative 11th. This is 15 times 10 to the negative 11th. And this is 20 times 10 to the negative 11th. Then, for 1 over D, that's running from 22 to 100. We only need to take up about half of the graph. So what we can say is, all right, let's go 25, 50, 75, 100. You could also go, actually, you know what? I think what we're going to do, just to expand that a little bit, is to go 20, 40, 60, 80, and then 100. That's going to be our graph there. Then we need to actually graph our quantities. I'm going to pause for a little bit and go ahead and do that because you don't want to watch me graph. All right, so once you have graphed these quantities, you need to draw a straight line that best represents your data. Now, let's say you graphed the wrong thing and your data showed a 1 over x curve, because that's the most obvious thing to do if you mess up part A. As long as you draw a best fit line that goes with it, even if that line has a negative slope, I think you're going to be able to get a point for that. But having done it right, you need to draw a best fit straight line, and you need to use a ruler with it. Now, I've got a fancy ruler with the computer, but you are allowed to bring a ruler with you into the AP exam. And if you don't bring a ruler with you into the AP exam, you can use the page of the test as a straight edge. That's the easiest thing to do. But there are a lot of ways to draw a straight line, but you need to make sure that line is straight and it's obvious that you are drawing that straight line. Now, once you draw your best fit straight line, you have to use that best fit straight line to calculate a dielectric constant for the paper. Now, in order to calculate that dielectric constant using the straight line, one of the things that this is telling us is to find the slope. Now, we have to talk about what the slope is equal to, but step one is finding the slope. So if we want to find the slope, you can use the linear regression in your calculator. That's allowed. But if you don't use the linear regression, you have to pick 2 points on your line that are not data points. So I'm going to pick this point. That's a really good one. It's not a data point. And I'm going to pick this point. Having chosen those points, you need to figure out their coordinates. So this is going to be 80, and then 17 times 10 to the negative 11th is that point, and this other point is going to be 8 and 4 times 10 to the negative 11th. So I have identified these 2 points. They are definitely not data points. They're just points on the line, good points, easy points to read. And so I'm going to get my slope based on those points, right? So that's going to be 17 times 10 to the negative 11th minus 4 times 10 to the negative 11th divided by 80 minus 8. So that slope comes out to be 1.8 times 10 to the negative 12th, and the units on that slope are going to be farads times meters. That's my slope. That's not the actual answer that I'm going for. I need to use that slope to find the dielectric constant for the paper. So based on what we graphed, what we have is capacitance equals A times kappa times epsilon naught over D. So what I have is capacitance times A kappa epsilon naught times 1 over D. Capacitance is my Y value, 1 over D is my X value, and all of this stuff is the slope. So A times kappa times epsilon naught is equal to the slope. It's important that you state that. College Board needs to see that you know what the slope is and it's not just the value that you're after. So kappa is going to be the slope divided by the area times epsilon naught. And so we have a value for slope. Kappa is going to equal 1.8 times 10 to the negative 12th farads per meter over the area, 0.06 meters squared, times epsilon naught, and that's on the formula chart, 8.85 times 10 to the negative 12th, and then all of the units on that are coulombs squared per Newton meters squared. Once you calculate that, the dielectric constant comes out to be, with my numbers, about 3.4, and that would be the dielectric constant that we got from the slope of the best fit line. Now, with a problem like this, here are a couple of things that are always true. You always need to make your graph. You always need to have a scale. You always need to label your axes and include units. All that stuff's worth a point. Really, if they tell you to do it, it's going to be worth a point. And drawing the best fit line is going to be worth a point. When you find the slope, you can find it by calculation, or you could use linear regression in your calculator. You just need to tell them I'm using linear regression to find my slope. Then you got to tell me what that slope is equal to and what you're going to do with it, always. This is how we find this, what the slope is equal to. That's an extremely important part of that. All right, moving on to the next part of the problem. The student now makes a capacitor using the same aluminum foil and places just one sheet of paper in there. Using the German dielectric constant, the student calculates the capacitance to be 18 nanofarads. The student uses this uncharged capacitor to build a circuit using a wire, a 36-volt battery, and 3 80-ohm resistors with an open switch as shown. Calculate a current in the battery immediately after the switch is closed. All right, so looking at this, if we want to look at the immediately after the switch is closed, what we want to look at is the time equals 0 circuit. Now, when time equals 0, my capacitor is empty, and it's going to act like a wire. So when time is equal to 0, my circuit looks like the battery, a resistor, a resistor. That capacitor is now acting just like a wire. It's not offering any impedance to the circuit. It's accepting charges, and at that instant, when time is equal to 0, current is going to appear as if it's flowing through the capacitor like it's not even there. And then we have that other 80-ohm resistor there. So for that time equals 0 position, if each one of these is 80 ohms, 80 ohms, and 80 ohms, if we sort of simplify that circuit, those two together give me 40 ohms. This one down here is 80 ohms. So if I want the current through the battery, that's going to be the total current. So 36 volts on the battery divided by 120 ohms total. That current through the battery initially comes out to be 0.3 amps. So that's my initial current through the battery. And then if I want the time constant for this circuit, time constant, if we're looking at sort of what this circuit looks like, is e to the negative t over tau. And we know that for a basic RC circuit, it's going to be e to the negative t over RC. So my time constant tau is equal to RC. Tau is equal to RC. Now that's the total resistance times the capacitance. So my total resistance here is 120 ohms times the capacitance of 18 times 10 to the negative 9th farads. So my time constant is going to be 120 times 18 times 10 to the negative 9th. Tau is going to be 2.16 times 10 to the negative 6. And that gives me, I believe, seconds. We could also express that as 2.19 times 10 to the negative 6. Sorry, 2.16. I wrote that down wrong. 2.16 times 10 to the negative 6 seconds, or 2.16 microseconds. Now, students A and B measure the time it takes after the switch is closed for the voltage off the capacitor to reach half its maximum value and find that it is longer than it is expected. Student A assumes that the capacitance value is correct. Would student A conclude that the resistance value is larger or smaller than measured? So if it's taking longer, what that means is tau is bigger than it's expected. Looking at the time constant, this e to the negative t over tau, the bigger that number tau is, the slower the e to the negative t over tau, the slower that thing approaches 0. Right? So the bigger tau is, the slower that reaches negative infinity, if you want to think of it that way. So the slower it takes. So if it takes longer to get to half the voltage, that means tau is bigger. And since tau is equal to RC in this case, if the R is correct, then that would be larger than expected. And so experimentally, what we would say is that circuit has more resistance. So experimentally, what we could say is that the battery is not ideal and has internal resistance we didn't account for. And because of that internal resistance, there's more resistance in my circuit. That's one way that we could talk about doing that. Student B assumes that the resistance value is correct. So student B would conclude that the capacitance value is larger than measured. So we're still talking about RC being bigger than it should be. If the resistance is correct, then the capacitance has to be bigger than what we measured. Now, looking at what could happen, the thickness of the sheets of paper could be thinner than expected, so the capacitance could go up. Really, it's any reason that you could legitimately find for the measured capacitance to be bigger. So if we say epsilon naught times kappa, then if D is smaller, if the paper is actually thinner, then it goes up. Or the measured area could be actually smaller in real life than was measured. It could be bigger in real life than was measured to give me greater capacitance. Just anything that's physically possible to account for what's going on there. All right, and that's the last of this question.